Here we are with lesson 5-2, Dynamics of Uniform Circular Motion. The objectives of this lesson are going to be to recognize and calculate centripetal force, as well as start to understand the dynamics of highway curves on banked and unbanked roads. All right, so let's get started with centripetal force. Just a few bits of information that we want to recall. So recall that an object traveling in uniform circular motion has centripetal acceleration, pointing towards the center of the circular motion. An important aspect of this that you need to understand is that centripetal is just referring to the direction of the acceleration. We're going to see today that we're going to also be talking about centripetal force. Centripetal force is not its own kind of force. It is just the direction of some force that is being applied, and that force needs to be applied by something. It might be tension in a string, it might be gravity, but that centripetal force must be applied by something. We learned in the previous lesson that centripetal acceleration can be found using the expression v squared over r. All right, you'll see this right here. In this case, v is the magnitude of the object's linear velocity, and r is the radius of the object's circular path. All right, when I say linear velocity, guys, I mean when an object is moving in uniform circular motion, it's going to have some linear velocity that is tangential to the uniform circular motion. All right, so now that we're talking about dynamics today, we have to bring in Newton's second law. Newton's second law is, of course, that the sum of your forces must be equal to mass times acceleration. All right. That said, if we're going to be referring to some centripetal acceleration, the fact that multiplying that centripetal acceleration by mass, which is a scalar multiple, means that whatever result we get, whatever force we deduce out of this, whatever force we calculate out of this scalar multiple, should be in the same direction as acceleration. And if acceleration is centripetal, then so should force. One thing I want to bring up is the fact that you might have a question come up that says, well, how do you calculate the centrifugal forces? And the very quick, clear answer is that in uniform circular motion, there's generally no centrifugal force. There's no real centrifugal force occurring. And even if you might think of centrifugal force might be occurring because of some centrifugal tension on your hand, that force is not being applied to the object that's in circular motion. It's just being applied to your hand in this case. That said, just to be very clear, centrifugal force is the opposite of centripetal force. It would be pointing directly outwards from the center of a circle as opposed to directly inwards towards the center of a circle. In experiment, we see that when a ball is let go after it was being swung around as it was tethered to a cord, it continues off after being let go in its own linear velocity, not some curved motion like you would see if there was actually centrifugal force. All right. That said, let's do our first example. It says, estimate the force a person must exert on a string attached to a 0.15 kilogram ball to make the ball revolve in a horizontal circle of radius 0.6 meters. The ball makes 2 revolutions per second. That's going to be the frequency, guys. And because period is the inverse of frequency, we could say that a frequency of 2 is going to give us a period of 1/2 or 0.5 seconds. Now, we're asking for force here, so that means we're definitely going to make use of this force equation for centripetal force, but we're also going to need to find acceleration to plug into that force equation right here. One thing is, in order to solve this, is that we're going to need velocity, but the question does not give us velocity, it just gives us the period. All right, so if the period is 0.500 seconds, we can very quickly find velocity using this relationship right here. Our linear velocity is going to be equal to the circumference of our circular motion, which is easily calculatable considering we have the radius, and we're going to divide that by what we have for the period. All right, so really quickly, if our circumference is 0.6, then we can multiply that by 2 pi in order to get circumference. If our radius is 0.6, sorry. So I can say that v is equal to about, this is a rough estimate, guys, about 3.77. That's going to be meters because it's distance, circumference. All right, and we're going to divide that by our period, which is 0.5 seconds. The result here is going to be meters per second, and that's exactly what we want because we're looking for velocity. So then the velocity is going to be equal to about 7.54. 7.54 meters per second. All right, guys. So now that we have velocity and that we were given mass and radius, we have everything we need in order to plug into our equation for force, our centripetal force. Let me zoom in here. our equation is going to be, or the expression that we need to actually solve is mv squared over r. So if I plug in the mass, which is 0.15 kg, 0.150 kg, and if we multiply that by 7.54 meters per second, square that quantity, and then divide that by the radius, which is 0.6 meters, well, then we should get a value that is equal to the force required to make all of this happen. That's going to be 7.54 squared divided by 0.6 and then multiplied by 0.15. Looks like about 14.2 newtons. And the reason why I know this is newtons is because, bear with me for a second, let's talk about it. This part right here gives us meters squared per second squared. And if we divide out 1 meters, then we're going to have acceleration, meters per second squared. And when you multiply acceleration by mass kilograms in SI units, you get newtons. And newtons is a measure of force, so everything checks out here. We're going to need 14.2 newtons exerted on the string if the ball weighs 0.15 kg, the radius is 6, and we want it to have a period of half a second. All right, let's keep going. Let's start talking about highway curves. Now I'm talking about when a car is actually traveling on a highway and it is traveling in uniform circular motion. So for simplicity, you can imagine that a car might just be traveling in a circle, but we also use this to model just partial circles or the curves that a car might round on an actual highway. Now, in this scenario, instead of tension or gravity, it's going to be friction that's pointing towards the center of the circle. Friction is the only thing stopping your car from sliding off as it makes a turn. And of course, you know that there's some inertia that wants to make you keep going straight, because everyone in here, everyone listening to this video has probably taken a sharp turn at some point and felt your body want to continue in its linear velocity, but the car kind of forces it in. Now, what forces the car in? The answer to that question is friction. Okay, so the road exerts an inward force on a car to make it move in a circle. The car exerts an inward force on the passenger. If there was no friction force that was centripetal, then when you try to turn, the car would just keep sliding forward in its linear velocity, and it wouldn't turn. So that is if the road is a level surface. One thing that we like to do in real life, though, is we like to bank our roads. And when I say bank, I mean we like to make it so that the outer edge of that curve is higher than the lower edge, so that our car is kind of on an incline. And let me show you a free body diagram that shows exactly what I mean here. In this case, you'll see that the outer edge of where the car's tire is higher than the inner edge of where the car's tire is. That makes the car have some kind of an incline. And what the important thing about what that does is that it makes the normal force point kind of to the side like this. It makes the normal force tilt inward towards the center of the circle. And that's very important for calculating centripetal force, because now that we have a force vector for the normal force that isn't vertical, we can now say that it has some horizontal component, and we can very easily calculate that horizontal component. And if the center of this uniform circular motion is over here somewhere, then that means that the centripetal acceleration is in this direction, parallel with the horizontal component of normal force. We can say it's not just friction keeping your car in that uniform circular motion. The horizontal component of normal force is now assisting in that endeavor. All right. So that said, there comes this question. How can we engineer our roads so that we don't have to be concerned about friction? Well, if this horizontal component to normal force, which is equal to normal force times sine theta, if that is able to match my expression for centripetal force, then we don't have to be concerned with how much friction the road has. Okay, we can just say that the normal force, or the horizontal component to normal force, will be enough. That said, let's go ahead and take that horizontal component to normal force and set it equal to how much centripetal force we need to maintain uniform circular motion. And that's exactly what you're going to see here. All right. So this is really powerful, because hold on, let's look at the free body diagram a little bit more. Notice that in this setup, in this free body diagram, the car should not be moving up or down. So that means these two vectors should be equal and opposite. Okay, they should be equal and opposite because there's not a vertical net force here. That said, I can say that the normal force times cosine of theta, which in this case should be equal and opposite to my gravitational force, which is mg, If this is a true statement, which I'm saying that it is based off of this free body diagram, then I should be able to solve for the normal force in one easy algebraic step. The normal force is going to be equal to mg over cosine theta. Now you might think, well, isn't the normal force usually just equal and opposite to gravity? Yes, generally that's true on a level surface, but this isn't a level surface. Our car is now on an incline. So that's going to kind of affect how much normal force we have. And in this case, normal force is going to be equal to mg times cosine theta. That said, I can actually use that and plug it into what I have over here, where I was trying to set the horizontal component of my normal force to the required centripetal force. And so if I go ahead and plug in mg, or let me see here. If I go ahead and plug in mg over cosine theta and multiply that by sine theta, when I set it equal to the required centripetal force, I'm able to cancel out mass. And this is something that you're going to be expected to do over and over again with different relationships on the AP Physics 1 test and just in physics in general. So now we have something very special on the left side, because if you remember from pre-calculus, sine theta over cosine theta gives us tangent theta, and that's exactly what we have here. So I can say that tangent theta is equal to, and don't forget about this acceleration due to gravity right here, okay? Tan theta is equal to v squared over r times acceleration due to gravity. And this is going to be really special because this is going to allow us to find out what angle we need to bank our curve at to maintain some, to match our centripetal force at specific velocities and radiuses of curvature. All right, that's going to be a very powerful equation for us, because we'll see that in our last example, part A is asking us to do just that. For a car traveling with the speed v around the curve of radius r, determine a formula for the angle at which a road should be banked so that no friction is required. All right, that's exactly what we just calculated up here at the bottom of the page above. All right, all we have to do is solve for theta. You plug in your values for v squared over r times acceleration due to gravity, and you take the inverse tangent of that. That should give you the angle theta required in order to maintain uniform circular motion. So then what does B say? B says, what is the angle for a road which has a curve of radius 50 and a design speed of 50 kilometers per hour? All right, let's use the equation we just derived, and let's use the information that was given. It looks like it gave us velocity and radius, and if you see here, that's all we need. So let's go ahead and put that velocity in SI units. V is going to be equal to 50 times, let's see, 5 over 18. 5 over 18 meters per second. That 5 over 18 is going to be the conversion factor from kilometers per hour to meters per second. So let me just do 50 times 5 and then divided by 18. Yeah, we have about 13.9 meters per second. And then we have a radius of 50 meters. All right, if we take what we just derived up here, we could say that tangent theta is going to be equal to 13.9 meters per second. This quantity is squared, and I'm going to divide this by 50 meters times 9.8 meters per second squared. All right, so in the calculator, let me go ahead and square my velocity. If I divide that by 50 and then divide it again by 9.8, then tangent theta in this case, and guys, this question was designed for 9.8, not the 10 meters per second squared, but you should still get a very close answer either way. So tangent theta is going to be equal to the 0.39 roughly. And it's good that we're actually canceling out all our units here. And you'll notice that we would, because we'd have meter squared per second squared on top and meter squared per second squared on bottom, because you want the solution to a trig function to not have any units. And from here, assuming that we have our calculators handy, then we can go ahead and take the inverse tangent of 0.39. And that will give us the angle that's required in order to maintain uniform circular motion in this setup, the angle in which we have to bank our road. Okay, so I can say now that theta is equal to 21.3 degrees. And just to be very clear, that's exactly what we'd need up here on the top of the page, guys. That's exactly what we need this bank angle to be in order to not have to rely on the friction between the tires and the road in order to keep the car in uniform circular motion. All right, guys, good luck. The problem set that I tied to this lesson is already posted, as well as the solution videos. Good luck. I'll see you in the next one, guys.